Hello, welcome to your Kaplan MCAT lesson about math on the MCAT. In this lesson, we're going to cover different ways that you can do calculations on problems that require it. Sometimes you have to do all the calculations, but a lot of times you don't have to do that many calculations. You can make minimal calculations. And then there's some problems you have to do no calculations at all for, even if it looks like you do. Remember, there's no calculator on the MCAT, so the less calculations you have to do, the more time that you're going to save. However, realize also, the MCAT is not directly a math test. There's just math on some problems to get at some other skill that you're showing off in that particular question. So don't let this math overwhelm you in any way. And the nicest thing about the MCAT in regard to the math is that there's no calculus. We're still going to be covering the skills that you need to know for the MCAT, as we always do in our lessons. And in this one, like we have been covering in all the lessons that begin with number 1, we're covering the science knowledge that you need to know about it, specifically in regards to questions that have math in them. The 2 learning goals that we're going to focus on are, first of all, how to solve MCAT problems with minimal calculations, and then second, how to develop the skill of really trying to find out whether or not you need to do math at all on certain problems. We'll show you ones where you do, and we'll show you how to find those ones where you don't really have to do the math as much. The science context through which we'll learn the skill of identifying when you need to use math and when you don't, and how to use that math as minimally as possible, are listed here. We've got fluids, translational motion, energy, and intermolecular forces. Also remember, we're not going to cover how each of these science topics works. That's what you do in your before class work. However, we will cover MCAT strategy in the context of these science topics. Now we're going to take a look at the strategy for science questions with calculations. Now it's still assess, plan, execute, and answer. However, we're going to give you some extra details that are going to go along with any given calculation type question. So first you're going to assess the question, and you're going to want to make the decision of whether or not you're going to have to do heavy math calculations in this type of question. Some indicators that there's going to be lots of math, or even just a little bit of math in a question, is if the answer choices are numbers, if there's a formula given in the problem, if there's measurements given in the problem, these types of things. Basically just if there's numbers in the problem at all. Now sometimes that means you don't have to do the math. However, it doesn't always mean that. So it's going to rely on the rest of the steps of the method, whether or not you actually have to do these calculations. So that's what you do during assess. You basically look for numbers. Then you move into the plan step, and your plan step is going to basically cover whether you need to do the calculations or not. And during this lesson, we'll talk about ways to realize whether or not you're supposed to do these calculations. If you do realize you need to do calculations, you will end up actually planning which formulas to use. And we'll show you this a couple times in the lesson. Then we come to the execute step. All you really want to do here is follow your plan. Make sure you get those calculations done if you need to do them. And then finally, you're going to answer. And the answer part, like we've been saying before, you could match your answer to the calculations, but you can also eliminate, or if you need to, guess. One important part about the answer step is to continually look at the answers while you're executing your math. If the right answer becomes obvious before you're finished with the calculations, then it's fine to go ahead and pick it and move on. You don't want to do more math than you need to. So we're going to start off with the first learning goal, and in this case we are going to see problems that definitely require math, but we'll show you how to do minimal calculation on them. We're going to start off with number 1, and we're going to do our assess, plan, execute, and answer step for sure on this one. And we want to take a look at the answer choices to determine whether or not we're going to need to use math. And we see that there are numbers in there, so we will have to do some sort of math, even if it's very minimal math. And we have a guess that it's probably fairly minimal math because there's another detail in each of these answer choices. That's the north and the south direction. So that's our assessment of this question. There might be some math, but maybe there's not tons that we have to do. Let's take a look at the problem here, and we see that there are some measurements in there. So we're still getting that indication of maybe some small amount of math. And the question says that there's a car traveling north at 25 meters a second, and then it takes 10 seconds for that car to stop. And they want to know the acceleration as the car slows down. So now we're thinking, okay, well, I know that 2 of these answer choices are going to easily be eliminated because they're going to have the wrong direction. So that's probably where I'm going to start. And then I will have 2 numbers to choose from between the 2 remaining answer choices, and it's probably going to be clear enough which one to pick. So overall, I can say there's probably actually not tons of math in this problem, other than maybe a little bit of reasoning. All right, so first I want to think about what I can eliminate because of the direction. If the car is traveling north and we have to use an acceleration to slow it down, we need that acceleration to oppose the movement of the car, to be in the opposite direction of the car. So we're looking for a direction that is southern. So we can get rid of two of our answer choices. We can get rid of answer choice A because it says north, and we can get rid of answer choice C because it says north. Now we're simply left with two answer choices that say south, which is correct, and now we're having to decide between B and D as our answer choices. Take a look at the numbers in each of these. In B, we have 2.5 meters per second, and in D, we have 25 meters per second. Now just ponder what answer choice D means for a moment. If that is our deceleration that we're experiencing in this problem, we were only going 25 meters per second to start with as our velocity. If we experience an acceleration in this car of 25 meters per second, that would mean that it would only take 1 second for the car to completely stop, because we take all of the velocity and get rid of it with that large of a deceleration. So we can get rid of answer choice D with that reasoning that has somewhat to do with the math, somewhat to do with reasoning, and we're really just left with answer choice B as our correct answer. All right, so there's very minimal calculation on that question, pretty much just math reasoning. Let's move over into number 2 and see a problem that does require us to do a bit more math, but we can still do minimal calculation on it. So in this one, in the assess step, we're looking and seeing that yes, definitely there are answer choices that have numbers in them, so I will have to do some math. And then our goal is to plan a way that requires minimal math. All right, so definitely numbers in the answer choices. It's definitely a math problem, and we need to think about what to do. Now recall, given that this is a kinematics problem, you know some kinematics equations. You probably just read about them in your review books when you prepared for this session. So these would be the equations that might come to mind when you are looking at a problem like this on test day. They're the standard kinematics equations, and the words vat, vax, and tax are the way that we have them listed in our review books, and a great way to remember them using those mnemonics. So looking at these equations and looking at the variables that you're given, there might be some different ways you could think of to do this problem. One of the ways that's often suggested is you could possibly use vax to solve for acceleration, and then use vat to solve for time. These are the kind of ways that you could go about doing this. However, on test day, when you realize that you're going to need more than one equation to solve a problem, generally that's a bad idea to do that much work for your math on the test. So, of course, you'd probably skip a problem like this and come back and do it later, but if you are here doing it later, it's better to try it a slightly different way. And they have actually given us a clue in this question. They've given us the word uniformly in the question stem. And anytime you see that word uniformly, that's a clue that there's a different way to go about this problem, because you can use average velocities. So we see the car was originally starting at 10 meters per second. We were brought to a halt over a distance of 0.5 meters. Halt means 0 meters per second. So that's a beginning and an end velocity. In that case, since I have the two different velocity points, I can actually take average velocity to just get a single velocity for this problem. What I mean when I say single velocity is basically add my two velocities together and divide by 2. Then, and you can see this in the equation that's appeared on your screen, just plug that single velocity into your very standard calculation for distance, where the change in distance, or delta x, is equal to your velocity, which is the average velocity in this case, multiplied by time. Distance equals velocity times time. Once you do that, you plug everything in and you'll be able to solve for the answer. So again, we're doing minimal calculation here. I'm not using two giant kinematics formulas. Instead, I'm just doing really quick calculation on average velocity and then using the distance formula to get time. Let's see how this math works out in the execute step. We're going to first solve everything for time using just our variables. And then we're going to plug all the numbers in. You see we've got half a meter for distance. We've got 0 and 10 meters per second for the two different velocities. And then we're going to be able to put that all together to solve for time. We see that the 2 times 0.5 works out to 1. And then we see 0 plus 10 meters a second is just 10 meters per second equals time. And so we get 1 over 10 as our answer, or 1/10, or 0.1 seconds as our total time for this. Looking at our answer choices, that clearly comes out to be answer choice B. Okay, let's go on to one more question. where we can demonstrate using minimal calculation to solve a problem. Now this one, again, in the assess step, I can see that all my answer choices have numbers in them, so I'm probably going to have to do some math. And I can look in the problem and see that I'm actually given some kind of formula in there as well. Flow equals 100 raised to the x. And actually, if you continue looking on through this problem, you get that flow is defined as 1,000 in the case that we're looking for to solve this problem. So really, they're giving us flow and what flow equals, and they're giving us what the flow is. The question stem actually gives us the equation we're supposed to use. And so that can actually be our plan for this step. I don't have to know an equation about flow at all. I don't have to know about fluid dynamics necessarily to solve this problem. I can just use what they're giving me. This is your minimal calculation for this problem, to realize that they're just giving you exactly what you need in this problem, and you just have to go ahead and solve for it. Now, solving for a variable when it's an exponent has a very straightforward approach. You do have to know how to use it here. And that very straightforward approach is to take the logarithm of both sides. So you're going to set up your equation, the 100 raised to the x that the problem is giving us, and we're going to set that equal to 1,000. So there's my setup for the equation. And then I'm going to execute the math that I know I need to do to solve this problem. I'm going to take the logarithm of both sides. And when you have a logarithm, you can move any exponent out to the front of that logarithm. So that's what we'll do here. Simplify log of 100 and log of 1,000 to 2 and 3. And that's how I get to this 2x equals 3 step here. Finally, I finish up the algebra, x equals 2/3 or 1.5, and I find that in my answer choices. Note the Kaplan tip at the bottom of the page. It's a reminder that when you do minimal calculation, you save yourself time on the test, and this extra time can go towards doing the tougher questions and getting those right as well. Great job on getting through Learning Goal 1. Now we're going to move on to the second learning goal of this lesson, where we're going to show you not only how to use minimal calculation, but walk through some problems that don't really even need any calculation at all, even if initially it looks like those problems will require a lot of math to complete. Starting with problem 4 here, we're going to assess it and see whether or not we're going to need calculations to solve this problem. So looking through, I do see numbers in my answer choices. However, the numbers are organized into what looks to be formulas. And then there is also numbers in the questions. So we're just basically setting up a formula and we don't have to solve it all the way. So no, there's not really any calculations to solve this problem. You just need to fill in the formula. So for what calculations are necessary, you really just need to fill in the tax formula. There's what the tax formula looks like as a reminder. It's a way to solve distance if you have an initial velocity, some acceleration, and some time. Now we're getting a lot of these variables from the question stem, and we can go ahead and fill them in the formula. So here's the steps on how to fill in the tax formula. You're going to plug in your 15 meters per second for velocity, your 2 meters per second for acceleration, and also note the negative sign that's being used in this formula. That negative sign is for deceleration. So we got to make sure that we're using that in the formula. Then we simplify as much as possible, and we see that the answer choice D ends up being our best answer. Another way to work through this problem is to eliminate your answer choices. You can get rid of answer choice B right away because the time is divided by 3 and there's no cause to divide time by 3 in this problem. You can get rid of answer choice C because they kind of forgot to leave the term for acceleration in answer choice C altogether. And finally, answer choice A is close to correct, but we get rid of it because it's showing a positive acceleration instead of a negative acceleration, and answer choice D still ends up being our best answer. Let's move on to number 5. Now number 5, when we look to our answer choices, we definitely see numbers in the answer choices, and we also see numbers, measurements given to us in the question stem, so it does look like there is some math that's going to be used to answer this question. So we need to think of what formulas we know, given that we have a patient who has a certain mass. We're trying to raise that patient up with a force, and we're given distance as well. So we're thinking of forces and distances, and especially thinking of this word hydraulically powered bed, we know that we're probably looking at some kind of force distance equation that has to do with hydraulically powered machines. So the equation that should come to mind is Pascal's principle and the conservation of work. You've got your force 1 times distance 1 equals force 2 times distance 2, maintaining a constant volume of that hydraulic fluid. And then we can just plug our numbers in. Remember, we're given 75 kilograms as our patient's mass, but that is not actually a force. So we'll have to change that mass into a force. The way that we do that is just multiply by gravity. So we can talk about the force downward that that patient has because of the earth pulling that patient towards itself. So that's the force downward, and then we'll say the force upward is what the bed actually has to supply, which we're given that that's 20 newtons. Our distance is 15 meters. We're seeing that distance is being accomplished by several foot pumps on this hydraulically powered surgical bed. And then we can see how far that 20 newtons over 15 meters is able to raise our 75 kilogram patient. So we'll start plugging in the numbers. Like we said, we first have to change kilograms into newtons, which we're accomplishing by multiplying that 75 times 10. We have our D1 as the variable that we're trying to solve, and then we have the 20 newtons times the 15 meters. We start solving the problem and we get that 750 times D1 will end up equaling 300. And so in the end, we'll have 300 over 750 equals our distance. So 300 over 750 is a difficult fraction to do in your head. It does, if you put it into a calculator, have an equal 0.4 meters, and that is our correct answer. However, that's a bit hard for calculations that you want to do in the MCAT. Rather, you should be using reasoning here. You should say that about half of 750 is just over 300. So if we're looking at 300 over 750, our answer should be just under 1/2 or 0.5. So your prediction when you go into your answer choices should not be exactly 0.4. It should be just under 1/2. And the only answer choice that is less than 1/2 in our answers is 0.4. So that's the way that you want to think about how to get to answer choice A, which is the correct answer on this problem. Finally, let's do one more problem here. Now, in the assess step, we're looking and seeing that our answer choices actually have a lot of variables in them, and then the question stem is giving us a bunch of formulas as well. So while it's not really a math problem, it is still an algebraic manipulation problem, and that's what we're going to have to do. In our plan step, we're going to have to come up with some sort of plan to do this algebraic manipulation. So looking through our question, we see the two formulas that were given, P equals QD and P equals alpha capital E. What we end up having to solve for is alpha, but just its actual units. So I see that alpha is in one of my equations and not the other, but luckily for us, both of these equations are equal to P. So in this case, we can combine the two equations and then rearrange to solve for that alpha. And this is what we've done in the math on the screen here, that the QD that the first P equals is equal to the alpha E that the second P equals. And then we can rearrange to solve for alpha. And then we have to start putting in our units. Looking at the answer choices, just to remind yourself what units we're looking for, we've got charge, we've got meters and kilograms and seconds. So that's generally what we're looking for. We're going to change Q to charge, because it's a function of charge. We're going to change D to just a distance. Our meters is our regular distance there. And then E, the electric field, we know is newtons per coulomb. And so we put that coulomb in there again. Then we'll do some algebraic manipulations here. We'll bring that coulomb up to the top, and then we'll leave newtons in the bottom half of the fraction, in the denominator. And we're also going to change newtons to its basic SI units, which is kilograms times meter per second squared, or mass times acceleration. Then we're going to do even more algebraic manipulations. We'll get rid of our two distances, which we find on both the top and the bottom of the fraction. And then we're also going to bring up our second squared to the top part of the fraction. When we do all this manipulation, we end up at coulomb squared times second squared divided by kilograms. And looking at our answer choices, answer B matches to the result that we found. Note the Kaplan tip on the bottom of the page reminds you that doing minimal calculations, or sometimes even no calculations, saves you time on the test, time which you can use to answer the tougher questions and maximize the number of points that you get. The review page here is going to cover again the assess, plan, execute, and answer steps in regards to science questions with calculations. So take a look at it, and remember you want to figure out whether you need the math, plan how much math you need to do, go through that math, and only go through the math as far as you need to match to an answer. One reminder, these questions with lots of calculations are there to weed out people who are going to spend too much time on those calculations and not get maximum points on their tests. So with this strategy, you can work towards not being one of those people. Also, if this lesson went over your head a bit, don't worry. There are a lot of formulas, and if you don't have them memorized quite yet, that is okay. In fact, once you do go study and memorize all the formulas that you need to for the test, feel free to come back to this lesson and watch it again and see how knowing the formulas works into your ability to decide what calculations to do and when to efficiently get through the test. Keep working on using these math shortcuts or even avoiding doing calculations altogether, and you'll be saving time in your test so you can use that time for the tougher problems and maximize your points, so we're always working towards that goal of getting you lots of points on test day.